Hey everyone, thanks for checking out this video of my A-10 6 degree of freedom flight simulator. Now this program was developed as part of the MAE 6510 Aircraft Dynamics and Flight Simulation course taught at Utah State University. Now there's a few different topics that I want to cover in this video and I've listed them out here. I'll touch briefly on the physics, a little bit about the aerodynamics model that's used in the simulator. Second, I'll talk about some of the additional features that I added that go beyond the baseline simulation that was required by the MAE 6510 course. And then lastly, a flight demonstration to show you how some of these additional features work in the simulation and have been incorporated into the overall experience. Okay, so let's jump right into this. Now the overall theme of this flight simulator, as I mentioned before, is an A-10 flight simulator. So you notice right up front and center, the ever awesome A-10 airframe. Now, this A-10 happens to be flying over some mountainous terrain, which is actually Google Earth data from Afghanistan, so it's theater terrain. Okay, so running behind the graphics, of course, are the actual physics and the aerodynamics model. Now, the particular aerodynamics model that we're using in this 6-stop simulation is a nonlinear aerodynamics model, which takes us up through the linear lift range all the way up to the point of stall, beyond which we use a piecewise stall model, which captures some of the different nonlinear effects that we have in that region. Now, you'll notice up and down the left and right side of the screen, we're printing out a number of important values. These include, of course, airspeed, angle of attack, side slip, the altitude at which we're flying, our bank and elevation angles, roll, pitch, and yaw rates, our elevator, aileron, and rudder deflections, as well as our throttle values and a number of other important parameters that we would want to know about our aircraft as we fly. Alright, so let's talk about some of the additional features which have been added to this program. One of my goals for this simulator was to add a number of different features and functionality which would enhance the overall experience of the user. And the first one that I added is this stall warning. So as you move up in angle of attack and you start to approach stall, you get this stall warning that flashes up on the screen. And in addition to the textual warning that the pilot would see in his heads-up display, there's also a tone that plays. The second feature that I added is a ground warning. This is similar to the stall warning in that it flashes a warning text to the heads-up display of the user, as well as playing a tone to get their attention. This particular warning comes on below a user-defined altitude threshold, and also when the aircraft is on a trajectory below the horizon, which would put them on an impact collision course. Alright, so the next feature that I incorporated into the simulator is G-lock. Now G-lock stands for G-force induced loss of consciousness. Now what this means is that as the user is flying along, if they happen to exceed a certain acceleration limit, which in this case is 8 Gs, the screen will turn black and throw up this G-lock warning, which effectively is the pilot blacking out, losing consciousness, and losing track of the attitude and orientation of the aircraft. And it's only after 5 seconds that the screen will reappear and the pilot can regain control of the aircraft. Okay, so the last feature that I'm going to talk about is the weapons armed feature. When a certain key is pressed, the weapons located underneath the main wing of the aircraft become armed. And you see that text flashed up along the bottom of the screen, letting the pilot know that his weapons have been armed. In addition to that textual warning is actually these spheres that you see going out ahead of the aircraft. Now what this is actually a parabolic prediction of the ballistic path that that bomb would take upon release. This parabolic prediction uses the classic ballistic equations to project out what the path of the bomb would be if it were to be dropped at that time. Now these equations use only an initial velocity and launch angle as well as that initial height of the aircraft. Now it's important to know that this ballistic projection does not incorporate some of the effects of drag and other losses that might be present. It's simply a tool for the pilot to use to predict that if they were to release the bomb in that moment, more or less what is the trajectory that that bomb would take. However, once the key is pressed to actually release that bomb, the actual bomb as it falls through the simulator is fully integrated and incorporates its own aerodynamics model and captures those different effects of drag and those other losses and is a more accurate prediction of the actual trajectory that that bomb might take. Alright, lastly, the flight demonstration, the part of the video that everyone I'm sure is excited to see. So in this flight demo, I'm going to go through each one of those key features that I mentioned beforehand, and so you can see a little bit of how those work in the actual simulation and add to that overall user experience that someone using the simulator might have. Also pay attention in the simulation to note some of the physics captured by the nonlinear aerodynamics model for both the aircraft and for the projectiles as they're dropped.